Bismillahirrahmanirrahim. Today we are going to discuss free radical in atmosphere with reference to environmental chemistry. Free radicals in atmosphere. Within the last 30 years, it has become increasingly obvious that all tropospheric oxidation processes are controlled by radical reactions. The radical pool maintaining the reactive flow determines the oxidizing capacity of the troposphere. Because the radicals are generated by photolysis, the degradation of trace gases in air proceeds by photooxidation. In particular, with the understanding of tropospheric carbon monoxide oxidation, the crucial importance of OH or hydroxyl radicals are realized, since no other species can oxidize carbon monoxide in the gaseous phase. So, air is a mixture of gases and suspended particulate matter. Industrialization and related human activities have infused into the environment increasing quantities of pollutants that have changed atmospheric chemistry noticeably in recent times. Now let's have a furtive glance at the percentage composition of various gases present in the environment. For example, nitrogen is present in the environment by 78.084% by volume. On the other hand, oxygen is 20.9476% by volume. Argon is present in the atmosphere 0.934%. Carbon dioxide, on the other hand, is present in the atmosphere 0.031% by volume. Neon, krypton, helium are present in the atmosphere by 0.01880 and 0.001140 and 0.00524% by volume respectively. Methane present in the atmosphere by 0.002% by volume. On the other hand, hydrogen is present in the percentage of 0.00005 and xenon is present in the percentage of 0.00087% by volume. So this table gives us a ready reckoner of different gases which are present in the atmosphere and their concentrations. In addition to these gases which are listed in the table, other gases such as hydrogen sulphide H2S, carbonyl sulphide COS, and nitrous oxide N2O emanated from the earth and biosphere are also found in trace amounts. Other oxides of nitrogen, for example NO, NO2, NO3, etc., collectively denoted as NOx. Oxides of sulfur, sulfur dioxide and sulfur trioxide, water vapors, volatile organic compounds VOC, and dust particles are other notable components of the air. The presence of ozone O3 at higher altitude is as important as that of oxygen for the life process, though in a totally different way. Free radicals define atmospheric chemistry. Atmospheric ozone chemistry is complex and fascinating, involving a number of free radical reactions. Much of this has been clarified and understood due to sustained efforts of a number of researchers during the last 40 to 50 years. P. Curtison, a Dutchman, M. Molina and F. S. Rowland, both these scientists are American, received in 1995 Nobel Prize in Chemistry for their work concerning the formation and destruction of ozone in the atmosphere. Much of the ozone drama is played out in the stratosphere, and a brief low-key sideshow is conducted at the Earth's surface, particularly in urban areas due to pollution. This story begins with the absorption of a solar ultraviolet radiation by oxygen molecules and proceeds as depicted in the following reactions. Oxygen, in the presence of ultraviolet radiation whose wavelength is less than or equal to 200 nanometer, is converted into atomic oxygen by the photolysis process. This atomic oxygen is very unstable and very reactive and reacts with oxygen to form O3, ozone, and some of the heat is produced during this reaction is adopted by the M. Here M is a third body which requires to take away the heat produced in the reaction. M could be a nitrogen molecule or oxygen molecule or any other species which is available at the site of the reaction. It could be anything. This heat, which we have already discussed in the reaction, is responsible for rewarming the atmosphere in the stratospheric ozone. At the height of 10 to 30 kilometers, the concentration of oxygen is just sufficient to absorb most of the ultraviolet radiations of a wavelength less than 200 nanometer. Above 30 kilometer, oxygen is spare, and hence the reaction presented in the equation which we have already discussed becomes insignificant. Now let's see the behavior of ozone near the ground level, or we can say that we are going to discuss the ozone in the lower tropospheric layer. Closer to the Earth's surface, a different route is available for the formation of atomic oxygen, which then follows the formation of ozone. As I told you earlier, that near the ground level, different routes are available for the formation of atomic oxygen, which later on reacts with oxygen molecule to form ozone 3. At this level, the 200 nanometer radiation is not available to dissociate the oxygen molecule. Okay? As it has been filtered off at high altitude, here the nitrogen dioxygen molecule or nitrogen dioxide in the presence of ultraviolet radiation whose maximum wavelength is about 400 nanometer, in the presence of heat energy of 400 nanometer, nitrogen dioxide converted into nitric oxide and oxygen. This is the atomic oxygen. This atomic oxygen then reacts with ozone to form the O3 molecule here. Other different routes which follow the sequence of reactions that contribute to involve the volatile organic molecules like hydrocarbons, acetone, etc., oxides of nitrogen and oxygen is as follow. Here RH, here in the equation, RH is represented the hydrocarbon, acetone or any volatile organic molecule, whereas I and dot is represented by the free radical initiator. So in this reaction, RH, which is a hydrocarbon molecule, reacts with the free radical initiator to form initiate I and H plus R radical, that is the alkyl radical. In the following reactions, alkyl radical reacts with oxygen to form ROO radical. ROO radical, it can also be called as peroxide radical, reacts with NO to form NO2 plus RO radical. NO2 then in the presence of HV radiations converted into NO plus atomic oxygen. Atomic oxygen reacts with oxygen to form O3. Here is a very important fact of a free radical reaction in the atmosphere, that is the aircraft emission join in the upper atmospheric free radical fray. In the tropospheric region of commercial aircraft flights, approximately about 15 km altitude, oxidation of carbon monoxide produced by aircraft will lead to the formation of ozone, as shown in the following reactions. HO radical or hydroxyl radical emitted from the aircraft emission reacts with carbon monoxide to form H radical, hydrogen radical and carbon dioxide. This reactive hydrogen or atomic hydrogen or a hydrogen in the form of a free radical reacts with oxygen to form HOO radical per hydroxyl radical. HOO radical then reacts with NO or nitric oxide to form NO2 and HO hydroxyl radical, nitrogen dioxide again in the presence of ultraviolet radiation nearly equal to wavelength of 400 nanometer converted into NO plus atomic oxygen. That atomic oxygen is very reactive and very unstable. So this reactive oxygen reacts with oxygen molecule to form ozone O3. Both these phenomena which is at the Earth's surface and aircraft of flight altitude cause smog in the respective regions of the troposphere. Now let's see the behavior of hydroxyl radical, an accomplished acylate of molecule by which of its high reactivity. Hydroxyl radical is a dominant primary radical species in the atmospheric chemistry. Although it occurs at only 1 parts per trillion, that is about 10 to 12 by volume, it plays a crucial role in initiating the reactions of gases emitted into the atmosphere by natural phenomena or human activities. Or human activities includes in the form of air emission or in the form of volatile organic molecules. Hydroxyl radicals is also called atmospheric detergent because it removes atmospheric chemicals or it reacts with other chemicals present in the atmosphere efficiently. Some of these reactions are shown below. For example, hydroxyl radical reacts with methane to form water and methyl radical. Similarly, Hydroxyl radical reacts with carbon monoxide to form a hydrogen radical or radical hydrogen and carbon dioxide. Hydroxyl radical reacts with ozone to form per hydroxyl radical and oxygen molecule. Hydroxyl radical reacts with nitrogen dioxide to form nitric acid. Hydroxyl radical reacts with nitric oxide or NO to form nitrous acid, NO2. Hydroxyl radical then reacts with this nitrous acid to form water and NO2, nitrogen dioxide. Hydroxyl radical then reacts with the volatile organic matter or particles of aldehyde to form water and carbonyl radical. The last one, this radical, which is RC dot double bond O, this is the carbonyl radical because this is C double bond O is a carbonyl group and carbon has a electron. The reaction in equation is appreciable to other hydrocarbons or many other compounds that has abstractable hydrogen, including the compounds that have replaceable chlorofluorocarbons at recent times, and these compounds are listed as CF3CH2F, CHF2, CHF, CHF2, CF3, CF2, CH3, etc., called hydrofluorocarbons, which do not contain chlorine in their molecule. Now let's see the important aspect of ozone chemistry in the stratosphere occurs after it has absorbed solar radiation of a wavelength 230 to 290 nanometer. Ozone in the presence of a wavelength which is nearly 230 to 290 nanometer is converted into oxygen molecule and atomic oxygen. This atomic oxygen is highly reactive and unstable and reacts with other molecules to form This removes virtually all the ultraviolet radiation in this wavelength range and to some extent down to wavelength nearly 350 nanometer, and ensures that this radiation is filtered out totally before reaching the troposphere. There are several other reactions that are also responsible for ozone destruction, and they are as number 1, atomic oxygen, which is produced in the last reaction, is highly reactive. It reacts with more ozone molecules to form oxygen molecule. Nitric oxide, NO, in the atmosphere reacts with ozone 3 O3 molecule to form NO2 and oxygen molecule again. Hydroxyl radical reacts with ozone molecule to form HOO radical and oxygen molecule. Per hydroxyl radical reacts with ozone again to form hydroxyl radical and oxygen molecule. However, ozone gets restored and its balance is maintained by repetitive occurrence of reaction. Thus, a life-friendly atmosphere has been preserved near the ground for millions of years. As industrialization advances in the last century, ever increasing quantities of halogenated organic compounds have been produced for use as solvents, refrigerants, aerosol, fire extinguisher, pesticides, and many more. A lot of these compounds escape into the atmosphere and they destroy the ozone and becomes the cause of ozone depletion. Many of them, particularly chlorofluorocarbons, are dissociated by stratospheric solar radiations to produce chlorine radicals, which are far more reactive than NO radicals and bring about very rapid destruction of ozone. Chloride radical reacts with ozone to form perchlorate radical and oxygen molecule. This perchlorate radical reacts with atomic oxygen to form ozone and chloride radical again. At the same time, perchlorate radical may react with NO to form NO2 and chloride radical again. Since perchlorate radical reacts with oxygen atoms needed to form O3 and generates chloride radicals, which will be back in action to destroy O3 or ozone molecules repeatedly for many decades until they are slowly removed from the stratosphere. The above chlorine initiated ozone decomposition reactions are highly detrimental to the ozone layer in its pristine protective role. Bromine radicals are also efficient in bringing down the ozone concentration by similar reaction sequences. The threat of ozone depletion has necessitated the rejection of CFCs as refrigerant, aerosol, etc. The results of the research efforts in these directions are apparent in such gadgets as CFC-free refrigerators, air conditioners, and similar cooling systems, which use hydrofluorocarbons as a substituent for CFCs. Now let's see the behavior of frozen free radicals and the ozone hole in Antarctica stratospheric layer. The ozone hole is a term used for the reduced concentration of ozone in the stratosphere as compared to the normal average value during a particular season of the year. For example, ozone concentration varies according to the time of the day, the season of the year, the nature and the amount of pollutant, and many other factors. The thinning of ozone layer in stratosphere over Antarctica during spring was noticed for the first time in 1982. Though attention was drawn to the ozone depletion power of chlorine radicals from CFCs as far back as 1973. Extensive research has shown that the main culprit in the decomposition of ozone is chlorine in the form of perchlorate radical. Chlorofluorocarbons escaped into the atmosphere during use stay for a long time in the troposphere. However, they are slowly transported into the stratosphere, where they absorb solar ultraviolet radiation. The high energy molecules dissociate and release the chlorine radicals. For example, CCl3F in the presence of ultraviolet radiation generates chloride radical and CCl2F radical. On the other hand, another chlorofluorocarbon, which is CCl2F2, in the presence of ultraviolet radiation generates chloride radical again and CClF2 radical. The chloride radical thus released will further react. At present, the ozone depletion is mainly restricted to the Antarctic region. This region attributed to this phenomena is as follows: that during the winter months, Antarctica receives no sunlight, causing the temperature to drop. The speed of westerly wind around the South Pole moving in a vortex increases and reaches about 350 km per hour. Because of the high speed, the air in the central region of the vortex experiences separation in a way from the surrounding air. The central air column of the vortex, covering most of the Antarctic region, receives no light at all, and the temperature keeps dropping. The clouds start forming at an altitude of 25 km in the stratosphere. The ice crystals in the clouds would trap the oxides of a nitrogen, perchlorate, chloride radical, and other radicals in their radical form as well. When the sun starts shining at the end of the winter, the trapped chloride radicals and other free radicals, along with VOC released, and which break down ozone according to the reaction described earlier. Here is the connection of free radical oxidation and the acid rain. We have already discussed acid rain in detail in a separate lecture. Now let's see here. The chemical substances in the troposphere have shorter lifetime due to high air density and the consequent high rates of molecular collision. They remain for a much shorter duration in this region as compared to substances in the stratosphere. This is because majority of them are washed off through precipitation events occurring only in the troposphere. Of the remaining, some are transported to the stratosphere and still others undergo oxidation or other reactions. We have earlier referred to a few of the reactions occurring in this region. Among other reactions, several acid-forming ones involve free radical oxidation processes. For example, H2S or hydrogen sulphide is oxidized to sulfur dioxide and further to sulfuric acid, ammonia to nitric oxide, which then further oxidized to HNO3, chlorohydro-carbons to HCl or carbon monoxide, etc. These products are brought down to earth by precipitation events in the form of the so-called acid rain. Measurements of atmospheric free radicals. The measurement of atmospheric free radical is a difficult experimental challenge. The concentration of hydroxyl radical at noon is nearly equal to 106 molecules per centimeter cube, and the lifetime is less than 1 second. For other radicals such as RO2, iodide oxide, bromide oxide, the concentrations are highly larger at nearly equal to 108 molecules per centimeter cube, or fewer parts per trillion. Techniques developed for the detection of such a lower concentration must be sensitive, highly selective, and good spatial and temporal resolutions. In polar regions, these radicals have been detected using laser-induced fluorescence. Long path differential optical absorption spectroscopy, which is also abbreviated as DOAS, and chemical ionization spectroscopy, which is abbreviated as CI. Both these techniques are used for the measurement of the concentration of different free radicals. Here at Leeds University, both the LIF and DOAS methods have been deployed in polar regions, and the reaction sequence used to describe hydroxyl radicals in the master chemical mechanisms. The first measurement of hydroxyl radical in the polar region were made at Palmer Station on the Antarctic Peninsula during the SCADE campaign. Because the hydroxyl radicals were removed from local sources of halogen species, the chemistry behaved as expected for a more pristine environment. The hydroxyl concentrations were very low, which means that during the 24 hours, the hydroxyl ion concentration is equal to 1.1 into 10 to raise per 5 molecules per centimeter cube. During the solar noon, its concentration nearly equal to 5 into 10 to raise per 5 molecules per centimeter cube. And there was a good agreement, that is 30%, with a model calculation showing that hydroxyl ion production was dominated by ozone photolysis, followed by the reaction of oxygen and its loss by the reaction with carbon monoxide and methane. These measurements can be taken as a base case. The main source of hydroxyl radicals were the photolysis of ozone and formaldehyde. Formaldehyde is used here due to the volatile organic matter, or as a volatile organic matter with important but uncertain contribution from HONO, which means nitrous acid, HNO2, and higher aldehydes. Carbon monoxide and methane were the main sink for hydroxyl radical, but model calculations suggest that other hydroxyl sinks are present, possibly oxygenated volatile organic particulate matter or volatile organic compounds. The effect of bromide oxide and iodide oxide radicals on concentration of hydroxyl radical and per hydroxide radical at Halle is quite striking. The largest source of hydroxyl radical is the photolysis of hydroxide iodide and hydroxide bromide. Photolysis are also important. HOI and HOBr are generated from the reaction when perhydroxyl radical reacts with iodide oxide radical and perhydroxide radical reacts with bromide oxide radicals respectively. Nitrous acid is also an important because uncertain photolytic source of hydroxyl radicals and high quality HONO or HNO2 measurements are required. There is now a considerable database of free radicals measurement at high altitudes using a range of techniques. Free radicals are ideal targets to test the accuracy of chemical mechanism. Oxidation chemistry mediated by free radicals of hydroxylene is more complex than expected for a remote pristine environment. Snow emission of radicals and oxides of nitrogen precursors increase the oxidizing capacity of polar environment, and halogen control all important aspects of the chemistry of the coastal Antarctic boundary layer at Helle during the summer methods. Here is a key question: is the vertical extent of halogen influence on the oxidative chemistry of polar regions? Recent satellite measurements suggest that elevated levels of iodide oxide radicals exist throughout the boundary layer. Further field work is planned in 2008 in the Arctic, that is the Hudson Bay, to further investigate ozone depletion events and the role of halogen species on the oxidative chemistry of the polar boundary layer.